Hello, my name is Jonah Wu, and this is my Physics 2211 Lab 1 Constant Velocity. The purpose of this lab was to observe the motion of an object at constant velocity and compare it to a computational model made in GlowScript. In the context of this experiment, this was observing the motion of a soccer ball rolling down a horizontal hallway. Two key assumptions for this experiment was that there was negligible air resistance and negligible friction force acting upon the ball as it rolled down the hallway, giving it a zero net force total. This leads me into the first fundamental principle of this experiment, which is Newton's first law, which states that an object at rest will continue to stay at rest, and an object in constant motion will continue to remain in constant motion unless a force is enacted upon the object. Therefore, if an object is moving at constant velocity, we know that the net force acting upon the object is zero. I also used Newton's second law, which states that the net force is the change in momentum over time, to derive the velocity update formula, which is that the final velocity is equal to v initial plus f net over m times delta t. And we can also use Newton's second law in various other formulas to derive the position update formula in terms of the average velocity, that the final position is equal to the initial position plus the average velocity times delta t, which in this experiment, the average velocity is constant, therefore we can say that it is the initial or final velocity. Here is a video of the tracker analysis performed on the soccer ball rolling down the hallway. And here is the GlowScript computational model that I compared this experiment to. As you can see, we initialized the ball with mass 0.43 kilograms and the initial velocity as this vector, which was obtained by measuring two time points in the tracker model. Here is the results of the computational model. For this experiment, we defined the system and surroundings and the initial conditions. For the system, it was a soccer ball. The surroundings of the system are the ground and the earth. And for our initial conditions, as shown in the GlowScript, the ball is moving at a velocity of approximately 1 meters per second in the negative x direction. And the ball is initially at position 0, 0, 0, and it has mass of 0.43 kilograms. Here is a comparison of the actual versus the predicted motion, where the blue line represents the motion that tracker observed, and the red is the predicted motion of the ball. As you can see, as both models approximate a model of constant velocity in the negative x direction. However, the actual motion appears to be slightly slower towards the end, especially as the velocity decreases slightly. However, the direction of motion remains the same. Therefore, this means that there were a few key errors in this experiment. If there were truly no air resistance or friction forces or any other net forces acting upon the ball during its motion, the graph of the observed motion would be identical to the graph of actual motion. However, this is not the case in this lab, as we saw. Therefore, in a real-world setting, it is extremely difficult to completely replicate in an ideal system to represent something as simple as constant velocity motion. Some possible sources of error. One huge source of error was the assumption of negligible friction force acting upon the ball, as well as air resistance. The experiment, which rolling the soccer ball, was done on carpet, which in reality has a non-negligible coefficient of friction and will eventually slow the ball down to a velocity of 0. Another key part was that air resistance could be non-negligible, but we could not really determine this. But in general, the assumption introduces a degree of error. Finally, one final source of error was failing to track the center of mass on tracker software correctly, because I had to approximate the location of the center of mass of the soccer ball in every frame to keep tracker let tracker track the ball down the hallway.